Here I've got this mid-1930s signal generator with its original documentation. It's a Readrite signal generator, model 554A. And Readrite was a trade name of the Triplet company, which is still around, incidentally. It's got an attenuator, ground, maximum and minimum outputs. It's got a very nice nickel-plated cover for the coil. All these got 5 different coils for the different frequencies. They plug in there. You can choose what type of frequency you want, and you can just grab coil. That's coil C. So we just plug in like this. And actually, that isn't the way it plugs in. There's 2 there that are the locking pins. There we are. That would go like that. Coil C. And you go to the documentation here. These graphs here. And you'd find coil C, which would be, I believe that's this, no, it's coil D. Turn it around here. There we have coil C. Now, setting the frequency is a bit complicated. Let's say you were at 50. Well, you'd go to this coil, and the coil goes from about 800 kilohertz, kilocycles, to 3900. Oh, actually not. The graph there, the curve of the graph, is what is the limits of frequency. So coil C would be from about 800 to, let's see here, 3100. So I've got this set at 50. So 50 would be right there, and that 50 would go down to 1500. That'd be 1500 kilohertz. So it's a bit complicated setting the frequency, but I would assume that once you've done it a few times, you get used to it. This signal generator goes from the beginning of the first curve on coil A is 100 kilohertz, and it goes up to 20 megahertz. So a reading of 100 on the highest coil would give you 20 megahertz, and a reading of 0 on the lowest coil will give you 100 kilohertz. This signal generator has an on-off switch, and you can set it for straight unmodulated or modulated. So this one would be a straight carrier, and that would be modulated by 400 hertz or whatever 1000 hertz tone. And here you have the level control or attenuator. It's got its original directions, which is quite amazing considering the age, and it's in very good condition. All the paper's in excellent condition. And how I decided on the age of this, I looked up documentation online, and it said that this model was made from 36 to 39. And looking at this form, it says 10735. So that'll be, I would assume, the 10th month, 7th day, 1935, when this form was printed. And maybe they started manufacturing these instruments in the winter of 1935. This one could be an early one. It's hard to tell. The only way is to look at the dates on the inside components, which I will do. A meter like this would have been designed for the technician to take out to service radios in the field. But looking at the condition that this meter is in, it's got almost no scuffs on the outside, almost no wear on the outside. It's just needs a good cleaning on the outside to bring back the color, the black of the leatherette case. But it's got amazing, it's got no rust to speak of on any of the metal pieces, and it's got no wear on the dials. Paint isn't scraped. It's just an amazing condition. That tells me that this was never taken out into the field. It probably was in a university, and it was just taken out by a professor twice a semester to do a demonstration on maybe some kind of electrical theory or something like that. Maybe it was in some university's electrical engineering lab, and it was just kept and used for demonstrations every now and again, and put up on the shelf for most of this time. I'm going to take it apart. Looks like there's 4 screws on the coil part, and the part with all the dials looks like it's another 4 screws, slot screws. Actually, there's 3 on that side. So we'll start taking it apart and look at what the inside looks like. This signal generator was originally powered by batteries. It would have used B+ batteries, which would give anywhere from 45 to 90 volts. And there's 2 tubes in there. They have 2-volt filaments, which could be supplied by a large dry cell, 1.5 volt dry cell. But it's amazing how clean. There's been no battery leakage in there or anything. So this was stored without batteries. So I'll take off the other side to see how that looks. The underside of the metal that holds the coils is in amazingly clean condition, very neatly cut out, very nicely made by a real craftsman. The inside is very nicely constructed soldered metal box, and there's no signs of just a little bit of whitish deterioration, no rusting or anything, just white oxidation. That's all you got there. And I'll just remove that and show you what the electronics looks like. A little bit of shoe dye would bring this box back to looking like new. It's in amazing condition. No rust. The leather handle is almost perfect. The latches look like they've had a little bit of, it's the only thing that's rusty in the whole thing. But they don't look, it's not a bad rust. It's like just like a rust of age. I wouldn't bother cleaning that off, but it's amazing how nice and clean the surface is. No wear to speak of. And the handle, hardly any wear at all. Just almost pristine. The electronics are very basic. It just consists of 2 triodes, a variable capacitor, a couple of capacitors, an attenuator, and I don't know what that, maybe there's more components. in this this like a box underneath the variable capacitor. It's like a tar box. There's some more, just a couple of resistors and the wafer switch. This is so simple, it's amazing it works. But you have two oscillators in there. So I'll probably have to draw out the schematic. But these two tubes are 30 tubes, which are just simple triodes. They are directly heated triodes, meaning that the filament is the cathode instead of an indirectly heated cathode, which is what you had later. These take 60 milliamps each on the filament, and they, if I recall when I looked at the specs of this tube, the cathode current is about 2.5 milliamps. That's well within the range of the batteries at the time, so it'll be easy to make a power supply out of this. I'll make a high voltage power supply, or B plus, out of a bunch of 9-volt batteries, and one simple flashlight battery will provide the current for the filaments. I just need to figure out a number of things on this, and then hook it up to some power and see what happens. On closer inspection of that thing I described earlier as a tar box, I can see it's a transformer, probably the modulation transformer. So the coils will set up, the coil and that capacitor, the variable capacitor, will set up a tuned circuit with one of the tubes, and then the other triode will produce a low frequency oscillation, like 100 hertz, and will just be combined in that modulation transformer. Very effective and very smart design, with so few components. It's amazing. That point out, one paper capacitor there is an Aerovox, but over here, interestingly enough, Readrite had its own capacitors, own house capacitors. This is mostly mica capacitors. That one there is probably paper inside, but there's a couple of micas. Probably that one and that one will have to be replaced, but I'll fire it up and see if it works. I won't change anything if it's been used so little. I'll see if that particular capacitor is shorted first, and if it gives the right frequency ranges, I'm not even going to bother, but we'll see. The layout is very nice and clean, well designed and well shielded. You can tell these tubes have hardly been used at all, because the writing on them is perfect, and there's no darkening anywhere inside the glass enclosure. Tubes darken as they age. I bet you these tubes have less than 100 hours on them. Nice to see something in such good condition from the 1930s. With these number 30 tubes, you've got two thicker ones which designate the filaments, and the other two are the control grid and the anode. These two wires here or the filament, and this red one is the B+. So I'll put one of these is tied to ground. So as you can see here, one side of the filament on the left tube is tied to ground. It's tied to chassis. So this one of these wires goes through the switch here, and when you turn it on, it switches in the filament voltage. The B+ is obviously always there, and when the tube starts to conduct, it starts using the B+. Because the B+, the red, isn't wired. It's wired directly to, it looks like, the modulation transformer. We have determined that on this tube here, pin 3, one side of the filament, which is pin 4, is tied to ground. Here's your other filament, which is tied to pin 4 on the other tube. And this one goes up here through the switch and comes out as the green on this side, which is your other filament switch, the high side of the filament. This one is tied to ground. So the grid, pin 3, goes through two capacitors, which are paralleled, and it goes to one side of the primary or of the transformer, and this side is tied to ground and goes up here and is this one here. My curiosity got the better of me, and even although I feel that the tubes are probably in excellent condition, I just thought I would test them anyway. So a 30 tube should be between, let's see here, 580 and 925 micromhos. See here, 570 and 900 microsiemens, or micromhos as they used to be called. So let's press the button. It's the top scale. So this one's 1,000 micromhos. I plugged the other tube in, and it's also 1,000 microsiemens. So that means they're both extremely excellent, as good as new. I couldn't see any documentation online anywhere for a Readrite 554A. So I wondered if the parent company, Triplet, might have a similar one, signal generator from about that time, that would be similar or the same. So I came across, I looked up Triplet, and sure enough, Triplet had a model 1231 signal generator, which is basically the same, except it's got one extra coil. The one I've got goes up to about 20 megahertz, and this one goes up to 30, so it's got 6 coils. Those might have been internal. I don't know what it looked like, but it has basically the same 2-tube arrangement with the modulation transformer, a modulation transformer switch, and a 4.5 volt battery and a 45 volt battery. And it's got the 0.01 microfarad capacitor. And apparently, I was mistaken. Those grid, what I thought were, I was right about the micas, but those are resistors in the grids. So it looked like capacitors. And There's one, it's in the low frequency oscillator, and it's 850 ohms. And this one has a couple of extra capacitors, which I don't see in this one. But it's basically the same circuit, and there's the variable capacitor. And so that'll allow me to fix this triplet, this Readrite one. Oh, incidentally, this signal generator must have been designed at the same time, maybe by the same guy. 1936. So the design for both of them was designed in 1935 or 36. When power is applied via turning on the on-off switch, B plus is applied to this anode and this anode, or plate, whatever you want to call it. They both start oscillating at their respective frequencies. This one, first tube, oscillates according to the setting of this, in which coil is picked here. When it's in the unmodulated state, you take the signal off here. This one is oscillating, and when you turn this switch to modulate, the signal is applied to this line, and it goes into this cathode circuit of the second oscillator tube, and they're combined. So your carrier is modulated at 1000 hertz, and you can take it off here where you have a 50 ohm output variable. You can change the voltage level of the output. I was mistaken on this particular one. The low frequency oscillator is not running on this one. It's a little bit different from the other one. The modulation transformer setup is very similar, except for the fact that in this one, when you switch the modulator switch in, you apply voltage to the plate of the modulator tube. So rather than having it running all the time like in the other one, this one, you have this switch just gets this one starting modulating when you put in the switch. So that would save you power. It's a kind of a better idea, actually. So maybe the Readrite was a little later. They figured out that you didn't need this modulator tube to be running all the time, only when you wanted modulation, because since the filament will be hot, it'll be instant on anyway, since you use less power. So that's one of the main differences between the two. When I'm switching through the bands using various coils, I can hear it working, but I'm not hearing any modulation when I switch that in. So, and also the output is very low. When I look at it on the oscilloscope, it's just minuscule, the output. It just looks like noise. So I'm going to have to check all the components and see if they are bad. Check all the resistors, and then I'll check the capacitors. So the oscillator, the one that produces the carrier signal, a high frequency oscillator, that seems to be working a little bit. I'm not getting a very high output. But the other tube, I put an oscilloscope on its, when I switch the modulator switch, don't get anything. So I think what we're going to have to check all these components. So that's what I will do. I'll go in there with a component checkers and see what we have. Here I'm going to check this 850 ohm resistor here that's in parallel with this mica mica capacitor, which they almost never go wrong. So here it's in the grid circuit of the low frequency modulator. So I'll check it right here. That's this one right here. It says 850. And I thought that one was a capacitor because I hadn't looked at a schematic, and it's 958 ohms. Good enough. So the next one I'm going to check is this one here, 50,000 ohms, which is in the grid circuit of the high frequency oscillator. And that's that one there. And we are measuring 53.4. That's within specs. So the next one I'm going to check is this capacitor here, 0.01 microfarads. That capacitor is right there, and I've taken it out of one half out of the circuit to see what value that it gives me. I've set this multimeter in its capacitance mode, and that use different terminals. And what I have is 0.019 microfarads. 0.019 microfarads from 0.01. That means it's doubled in size. But I'm not going to worry about that too much right now, because I don't think that's what is keeping the circuit from oscillating. So this, all these, the tubes are strong. Everything that matters in that circuit, as far as resistor values and everything, seem to be working okay. They seem to be within specs. I checked out the modulation transformer. Both coils seem to be even. They're about a couple of hundred ohms. And the plate voltages are okay. The switches seem to be okay. I didn't bother checking out these mica capacitors, because they are very rarely do they ever go. And this wouldn't affect it. This wouldn't keep it from the fact that this 0.01 microfarad capacitor has doubled its value. That wouldn't keep it from oscillating. It's got the right voltages. Down here, I checked that resistor. That wouldn't keep it from oscillating. That would just block it from going out here. This was missing. This 0.003 microfarads, which is 300 picofarads. This resistor here checked out to be okay. It's about 850 ohms. This here is measures 50 ohms from here to here. And so I changed that just because you need that to bypass the signal. If this was working, I'd get a very, very low signal out there. So this needs to be here to allow the signal to get out. So someone had been, I don't know, that you could see that it had been desoldered. So someone was working on this area and probably took the capacitor out thinking that they could fix it or something. But I just put one in there. And so that's down there, right there. And that will allow the signal to go into the output circuit. Now, what I think is the problem, I've experienced this with quite a few old radios. This is just something you have to suspect in these really old radio and pieces of equipment. These, all the solder joints oxidize, and it will keep a circuit from working. You never know if these old, in the old days, they quite often just used acid solder, and it worked fine for a few years, but eventually it caused the joints to oxidize and make bad connections. So that's what I think is the problem with this. So I'm just going to resolder every solder joint, and there's a good chance that will solve the problem, because everything else seems to be okay. Everything is in the right place. The tubes are very strong. The resistors are fine. The mica capacitors are the last thing I would look for. So, and I don't think that this capacitor would affect anything. So I'm going to resolder all the connections and even add some solder and see what happens. So I soldered all the circuit, soldered all the joints and added a little bit of solder, and voila, it works. It's this is taking, I'm taking this, it's 20 volts, so this is 40 volts peak to peak, and it's 1000 hertz, and I'm taking it at this point in the circuit, right on the plate, right here, right on the plate of the 1000 hertz oscillator, and that's where it is, right there. You can see the probe right there, right there. So now I'm going to check and see how the RF is. So now I'm taking a look at the signal right here. This is one right here, and that is at the top of the capacitor, right at the tuned circuit, and I'm getting a nice symmetrical waveform, 462.2 kilohertz. I'll change the setting. Goes down to 293 and goes up to 909.1 kilohertz. We'll hit auto setting, and there we have a nice signal that's 60 volts. No, is that 20 volts per division? Doesn't make sense. 60 volts peak to peak. Anyway, that is nice clean waveform. Go down in frequency a bit and bring it up to modulation, although it might not, you might not see too much modulation on the output here because it's at a tuned circuit. Oh yeah, it's going up and down. It turns it on and off at so now I'm going to take a look at the signal at the output. So here we are, we've got a radio, and it's picking up the signal, modulated signal, and it's working very well. That's at about 1400 megahertz. The radio's set on 1500 kilohertz. So that's just jumping around because it can't lock onto anything, but it's 1500 kilohertz. The signal generator seems to be working very well, so I'll just leave it as it is, and the only thing that I will do once I put it into the case is to make a power supply for it, and I'll leave that for the next video.